Jai Hind. Today we are going to discuss recurrence relations. This is one topic of 5th unit of discrete mathematics. The different contents I am going to cover are: what is recurrence relation, what is simple recurrence relation with constant coefficient, then linear recurrence relation with constant coefficients, and different methods of solving the recurrences. My PPTs are based on the book of Kenneth Rosen, Discrete Mathematics and its Application. So let us start with our topic of recurrence relation. Firstly, we will start with recurrence relation and then we will proceed with the methods of solving recurrences. What is a recurrence relation? A recurrence relation for the sequence an is an equation that expresses an in terms of one or more of the previous terms of the same sequence, namely a0, a1, a2 up to an minus 1 for all integers n, where n is greater than equal to n0 and n0 is a non-negative integer. So what is recurrence relation? In recurrence relation we represent a sequence. The sequence is represented in its previous terms. For example, an, the nth term, can be expressed in terms of an minus 1 or an minus 1 and an minus 2 and so on. What is a sequence? What the sequence is for the recurrence relation? A sequence is called a solution of the recurrence relation if its terms satisfies the recurrence relation, and reversibly a recurrence relation is said to be recursively define a sequence. So sequence is solution to the recurrence relation, and recurrence relation recursively defines the sequence. So let us understand the concept with an example. So what is given here? Here we are given a sequence containing the terms an. So what is my sequence? That is an. What is the recurrence relation given? An can be represented as an minus 1 plus 3, where n is having value 1, 2, 3 and so on. So what is done here? The nth term is expressed in terms of n minus 1th term, and there is one more term here, that is plus 3. It is only a constant. So if we know n minus 1th term, I can calculate nth term. This is a recurrence relation. So here what is given? a0 is equal to 2. When we will be given some recurrence relation, there will be some initial conditions which are also called base values. So what is a0? This is the initial condition, because we are having the terms a0, a1, a2, a3, and a0 is not having its previous term, it is the first term. So this is the base term, initial condition or base values. So we will be given this initial value and the recurrence relation. Now for n is equal to 1, 2, 3, all the values we can calculate from here. So if I talk about a1, what will be my a1? It can be calculated from a0 using the recurrence relation. What is the recurrence relation? an minus 1 plus 3. So when I put n is equal to 1, because 1th term I am calculating, so it will be a0 plus 3. So what value I am getting here? That is a0 plus 3, that is 5. So I got the 1th term. Now if I consider the second one, a2, it is sum of its just previous term plus 3. So what is my previous term? That is a1 plus 3. So what I am getting here? That is 8. Now what is a3? a3 is 3 plus the previous term. What was the previous term? That is a2. a2 plus 3, that is 11. So we are getting the nth term from n minus 1th term. Okay, so this is one recurrence relation, example of recurrence relation. So I am having the recurrence relation, and with help of that recurrence relation I can find the sequence, and this sequence is the solution to the recurrence relation, and the recurrence relation is recursively defining this particular sequence. Same way we will get n is equal to 4th term for putting n is equal to 4, 5th term by putting n is equal to 5, and so on. So, this is my recurrence relation. Another example is Fibonacci sequence. The Fibonacci sequence F0, F1, F2 is defined by the initial condition F0 is equal to 0 and F1 is equal to 1, and the recurrence relation is Fn is equal to Fn minus 1 plus Fn minus 2. What is Fibonacci sequence? In this, nth term is summation of n minus 1th and n minus 2th term. So, that is my recurrence relation. 0th term is given as 0, 1th term is given as 1, and 2th term I can calculate from this recurrence relation. What will be my next term? That is F2. It will be F2 minus 1 means F1 plus Fn minus 2 means F0. So, my next value will be, what is F0 given? 0, F1 given 1 and F0 0. So, I will get 1 value. What will be F3? That will be F2 plus F1. It means 1 plus 1, that is 2, and so on. So, this way we can represent a sequence using recurrence relation if the terms are related to each other, if one term can be expressed in terms of the previous term. So, this is our recurrence relation. Now, we will talk about solution of these recurrence relations, because recurrence relation is having the solution which is the given sequence. So, one method we are taking here just to understand the recurrence relation, that is substitution. So, what is the substitution method? Let me take this example. I am given a recurrence relation, I need to solve it. So, what will be the solution to this recurrence relation? What it is given? A0 is equal to 1 and AK is equal to K minus 1 plus 2. It means kth term is K minus 1th term plus 2. So, now we need to solve. So, one method is substitution. So, if we start substituting the value, what we get? A0 is A1 is equal to A0 plus 2 by putting K is equal to 1 as we did on the last slide. So, here K we have put as 1. So, what I got here? A0 plus 2. Now, what is A2? A2 is A1 plus 2, previous term with adding 2. And what is A1? A1 is calculated previously. What is that? A0 plus 2. So, what we got here? What we are getting here? A0 plus 2 plus 2. So, we are getting A0 plus 4. So, what we are doing? We are substituting the values. A3. A3, third term will be 2th term plus 2. So, what we have taken? A2 plus 2. So, what we are getting here? What is A2's value? That is A0 plus 4. So, here we have substituted A0 plus 4. So, what we are getting here? A0 plus 6. So, this way we will substitute the values. So, what we are getting here? A0 is A1 is A0 plus 2 and A0 is given as 1. What is A2? A2 is A0 plus 4. What is A3? A3 is A0 plus 6. What is A4? A4 is A0 plus 8. So, if we see these values, we find that 4, 8. So, it means 2 into 4, 8. 3, 6. It means 2 into 3, 6. So, kth term we can represent as A0 plus 2k. This is my A0 value. This is A1. A1 is 1 into 2. A2 is 2 into 2. A3 is 2 into 3. A4 is 2 into 4. So, we can represent AK is equal to A0 plus 2k. Okay, and A naught is given as 1. So, what solution we got? AK is equal to 2k plus 1. So, we have solved it using substitution. We are going on substituting and then we are checking what the pattern is. What pattern is made out of these values. So, we are able to observe that the pattern is 2 into the number of terms plus A naught. A naught is my initial condition, the base value, that is 1. So, I got this substitution answer. Another, A1 is equal to 1, AK is equal to 2AK minus 1. So, we are taking another example to understand the concept of substitution. So, if I substitute this for second value, that is A2, what I got? A2 is twice the previous term plus 1. What is my substituted value? 2A1 plus 1. Okay, now if we put the value, substitute the value of A1, we got it 2 into 1, that is 3. For A3, we are substituting 2A2 plus 1. What is A2? A2 is 2A1 plus 1. So, what we are getting here? 4A1 plus 3. What we are getting for A4? 8A1 plus 7. A5, 16A1 plus 15. So, when we are putting this A1 value, we are getting the substituted result as 3, 7, 15, 31. Okay. So, when we are getting these values, now we are able to observe the pattern. What is the pattern? If it is 2, it is 3, it means 2 square minus 1. If it is A3, so I am getting A7, it means 2 to the power 3 minus 1. For 4, I am getting 15. So, what pattern I am getting? I am getting a pattern of AK is equal to 2 to the power k minus 1. So, this is substitution method. We will find out the pattern and that will be the solution. So, this is one of the methods. We will go on substituting and we will observe the pattern, that will be the solution of the recurrence relation. Now, every time we are not able to observe these patterns directly, so we need some other method. So, now we will discuss another method for solving the recurrence relation. So, here I am taking the general definition of linear recurrence relation. By linear means I am having the power as 1 only, linear powers. So, what we are taking on this particular slide, we are starting with homogeneous solutions, homogeneous recurrence relation. A linear homogeneous recurrence relation of degree k with constant coefficient is a recurrence relation of the form an is equal to C1 into an minus 1 plus C2 an minus 2 plus C3 an minus 3 and so on. The last term is Ck plus an minus k. So, an is defined in terms of n minus 1th, n minus 2th and up to n minus kth term. Okay, and this Ck is not 0. If Ck will be 0, it means this is not required, it means it can be defined in terms of up to n minus k minus 1th. So, when we are saying that it is defined as n minus kth term, it means Ck will be non-zero. And what is C1, C2, Ck? These are our real numbers. So, when we are taking up to k terms, we call it degree k. If we recall the previous example, in one of our examples, we were having an is equal to an minus 1 plus 3. In this, we can see that an is defined as in terms of an minus 1 plus 3. Okay, so here the degree is 1. if we recall our Fibonacci series, Fn is equal to Fn minus 1 plus Fn minus 2. So, it is defined in previous two terms. So, degree will be 2. Now, what we are going to take, we will go on taking this type of recurrence relation. In this type of recurrence relation, what we are having, an C1 an minus 1, n minus 1 to n minus k. So, we will not consider this type of equation, recurrence relations. We will consider homogeneous, in which we are not having this constant term. Okay. So, what type of recurrence relation we will consider? Like Fibonacci series, if we see this, in this Fn is defined in terms of Fn minus 1 and Fn minus 2, two terms. So, this is of degree k. Now, there is no other term. An is defined as C1 an minus 1 up to an minus k, degree k. So, this is homogeneous linear recurrence relation. So, now firstly we will consider these type of relations, recurrence relations, and we will solve that using different methods. Okay. So, let us start with the linear homogeneous recurrence relation of degree k. So, we are going to solve linear homogeneous recurrence relation with constant coefficient. Coefficients are also constant. The basic approach for solving linear homogeneous recurrence relation means we are looking for a solution of the form an is equal to r to the power n. So, what is our general solution that we want? An is equal to r to the power n. So, when we are trying to find this type of solution, okay, where r is constant, what does it mean? It means it will be as it is solution to the recurrence relation, it means it will satisfy the recurrence relation. So, it is a solution of the recurrence relation an is equal to C1 an minus 1 plus C2 an minus 2 up to Ck an minus k, if and only if Rn satisfies the an is equal to Rn satisfies the equation. It means r to the power n is equal to C1 r to the power n minus 1 plus C2 r to the power n minus 2 and so on up to last term, that is kth term, Ck into r to the power n minus k. So, what we have done, in place of an minus 1 or an minus 2, we have put the assumed solution that an is equal to r to the power n. So, it is satisfying it. So, when we find this type of equation, it is homogeneous equation. Okay. So, when we will have this type of equation and we divide both the side by r to the power n minus 1 term, so what we will get? We will get the characteristic equation of that particular recurrence relation. What is this? This is my characteristic equation of the given recurrence relation, characteristic equation. So, when I will get this characteristic equation, we can find now the roots of this. So, those are called characteristic roots. Now, these roots will represent the solution in the given form. So, what is our aim? Our aim is to find the solution an is equal to Rn. So, what we will take for this constant r, that will be obtained from the characteristic equation. The characteristic equation will have the characteristic root that will be inserted here to find the final solution. So, let us try it. Now, when I am saying that there is characteristic equation, so there are different possibilities for the roots. For example, if I am getting an equation which is having two roots 1 and 2. So what is the nature of these two roots? These are distinct. Okay, so distinct roots rule will be there different, and it may be the case that the equation is having two roots which are same 1 and 1. So in that case we will have single root. So we will take a different possibility, different equation we will get for the solution. The sequence nth term will be different, that is an will be different. So let us take the examples one by one and the concept. So first one is the roots are distinct. Okay. So let C1 and C2 be real numbers. Suppose that r square minus C1 r minus C2 is 0. It means the characteristic equation which is taken here as quadratic equation. This has two distinct roots r1 and r2. Then an is a solution of the recurrence relation. An is equal to C1 an minus 1 plus C2 an minus 2 if and only if an is equal to alpha 1 r1 to the power n plus alpha 2 r2 to the power n for n is equal to 1, 2, 3, where alpha 1 and alpha 2 are constants. So we will see that if the roots are different, then how can we find the solution? So general solution will be alpha 1 into r1 to the power n plus alpha 2 r2 to the power n. Okay, so this will be the solution. Now let us understand how do we solve a recurrence relation. The recurrence relation given here is of degree 2. So we are given two initial conditions a0 and a1. a0 is given as 2 and a1 is given as 7. So now we will learn on this particular slide that how do we solve a recurrence relation with distinct roots. So my recurrence relation is given as an is equal to an minus 1 plus 2 an minus 2. So what we said? We said we will have this type of solution. Okay. So what we assumed, an is equal to r to the power n. By substituting this assumed solution, by substituting, what we will get? By substituting, we will get an is equal to an minus 1 plus 2 an minus 2 as r to the power n, because an is substituted with rn minus 1 is equal to r is substituted with rn, an minus 1 with rn minus 1 and an minus 2 with rn minus 2. So simply what we have done, an is equal to r to the power n, an minus 1 as rn minus 1 and an minus 2 as rn minus 2. If we see here, n minus 2 is common in all. So we will divide both sides with n minus 2. So what I will get here by dividing n minus 2? Here n minus 2 will be square, r square is equal to r plus 2. Now taking these to the left side, what I will get? R square minus r plus 2 is equal to 0. So when I solve this particular equation, I will get r square minus 2r. This minus will become minus on this side. When we will bring on left, so it will be minus r minus 2 is equal to 0. So it will be minus 2r plus r minus 2 is equal to 0. So simply I am getting r minus 2 into r plus 1. So what I got from here? R is having two roots, 2 and -1. What are the roots of 2? Characteristic roots of this particular recurrence relation, that is 2 and -1. So what will be the solution? The solution will be alpha 1 R1 to the power n plus alpha 2 R2 to the power n. So what will be my solution? My solution will be An is equal to alpha 1. What is my first root? 2. So 2 to the power n plus alpha 2. What is my second root? That is -1. So it will be -1 to the power n. So what was the root? Alpha 1 into R1 to the power n. R1 was calculated as 2 plus alpha 2 into R2 to the power n. So what is the second root? R1 is 2 and R2 is -1. So that we have inserted here. Now this is the solution, but what is there given there? Two constants, alpha 1 and alpha 2. So how to calculate these two constants? How we will calculate is, so we will see from here that we are given two terms as A0 is equal to 2 and A1 is equal to 7. So if I put value n is equal to 0, so what I will get? 2. So I am putting value n is equal to 0. So I am getting the equation as 2 is equal to, now it is 2 to the power 0, it means 1. So it will be alpha 1 plus -1 to the power 0, it means alpha 2. So from here I get this equation. Now if I put value n is equal to 1, because I have been given in question A1 is equal to 7. So if I put value 1, so what will I get here? The A1 term will be 7. Now n will be substituted with 1. So this will be 2 to the power 1. It means 2 alpha 1. This will come as 2 alpha 1. Same way here, -1 to the power 1, that is -1. So minus alpha 2. So I got two equations for alpha 1 and alpha 2. Okay. So from here and here I can solve alpha 1 and alpha 2. If I add these two, by adding these two, what I am getting? 9 is equal to 3 alpha 1 and alpha 2 plus alpha 2 and minus alpha 2 will get crossed. So I am getting alpha 1 as 3. So my alpha 1 value has come to be 3. Now from here I can calculate alpha 2. Alpha 2 will be 2 minus alpha 1. 2 minus alpha 1. So 2 minus alpha 1 means 2 minus 3. So it will come as -1. Okay. So from here we got the values of alpha 1 and alpha 2 also. So I got the recurrence relation solution sequence, that is An, and so I'll put values of alpha 1 and alpha 2 and I will get the final result. So what will be my nth term now? This is my solution, final solution. So what will be my nth value? That is alpha 1 into 2 to the power n. What is alpha 1? Alpha 1 is 3, it means 3 into 2 to the power n plus alpha 2. What is alpha 2? -1. -1 to the power n. So this is the solution when we are having distinct roots. Now we can have other case also. What is the other case? The other case is all the roots are not distinct. So the concept of non-distinct root means similar roots we will understand with help of one single root. So for single root we are taking this particular example. In this particular example what we are having, we are given a recurrence relation. Let C1 and C2 be real numbers and R square minus C1 R minus C2 is 0, has only one root R0. So what we considered here, we considered here that we have a quadratic characteristic equation, and for that we are having only one root, multiplicity with different multiplicity, means single root is there and it is having twice. So for this we are having this sequence an as the solution of the recurrence relation if and only if an is equal to alpha 1 r naught to the power n plus alpha 2 n r naught to the power n. So what is the difference? There we were having two distinct roots, that is alpha 1 and alpha that is r1 and r2. So what we took, alpha 1 r1 to the power n plus alpha 2 r2 to the power n. But here we are having single root r naught, but it is occurring twice. So we will have alpha 1 r naught to the power n plus alpha 2 r naught to the power n with this multiplication of n. What we are multiplying here? N, that is showing the multiplicity. So if we consider this particular example to show this, so for this we will get the characteristic equation as r square minus 6r plus 9 is equal to 0. So when we will get this by putting the an is equal to rn, we will get this characteristic equation, and for this we are getting the root r minus 3 whole square is equal to 0. So my roots are 3 and 3. So it is single root with multiplicity 1. So what we will have now, our solution will not be like the previous one, it will be an is equal to alpha 1 3 power n plus alpha 2 into, showing the multiplicity n, alpha 2 n into 3 to the power n. So this we are having in case of single root. Now how we will calculate alpha 1 and alpha 2? We will calculate alpha 1 and alpha 2 same as we have done on the previous slide with help of the initial conditions. We will put once n is equal to 0 and a naught is given as 1, and then n is equal to 1 and value is given as 6. So by entering those values we will get the answer as of alpha 1 and alpha 2. That will be the final answer. The two constants can be calculated from there. So these are the ways to check to find the example with single root or distinct root. So let us generalize in next slide. Let me say we are having k distinct roots. The two questions that we have solved on the previous slides, those were for quadratic characteristic equation, but it could be the case that you are having a higher degree equation, not quadratic, so you get different root. So let me take the case of k distinct root. So what will be my proposed solution? My proposed solution will be an is equal to alpha 1 into r1 to the power n plus alpha 2 r2 to the power n plus so on alpha k into rk to the power n. This is for distinct root. In this we will have constant term multiplied by root to the power n. This is for distinct roots, and when we are not having distinct root, it means we are having many roots and they are having different multiplicities. For example, let me say r1 occurs m1 time, r2 occurs m2 times, rt the tth root occurs mt times, and so on. So if we are having t roots and all are having different multiplicities, so what will be my proposed solution? My proposed solution will be an this to the power r1 to the power n. r1 is my first root. Now what I said, it is occurring m1 times. m1 times. So what we need to show? We need to show this multiplicity. So we will take constant plus constant into n plus constant and so on till m1 minus 1th term. As we saw on last slide, that was occurring 2 times, and we took the multiplicity up to n, that is 1 plus n we were taking. So in this case what we will take up to m1 minus 1. Same way R2 is occurring for m2 times, so it will be up to m2 minus 1 and so on. This is our distinct our root with we are having multiple roots and with multiple distinct multiplicities. So this was about our solutions of linear homogeneous recurrence relations. So in this particular video we talked about the recurrence relation, and then we talked about we can solve the recurrence relation using substitution method. We can find out the general term. For example, we calculated 2k is equal to AK is equal to 2k plus 1 in our first one of the examples. Then we took the case of linear homogeneous recurrence relations with constant coefficient, and we discussed how the homogeneous recurrence relations can be solved in different cases of distinct root and similar roots. Thank you. Jai Hind.